Okay, so good evening. Now you make sure you open for the SPSS. And make sure you stand by with the SPSS. Okay, I'll give you maybe 30 seconds. Yeah. Okay, so and then also the data file. Yeah, data file that we also use here in the previous class. Okay, so so now I share the screen, then we can start. Yeah. Okay, so for those who came a little bit late, make sure you let me know and then my attendance. And then one more thing, we already decided just now, starting tomorrow, yeah, for the weekday class, we start from 7. Yeah, 7:30, 7:30. Sorry, yes, correct. 7:30 until 9:30. Okay, still 2 hours. Okay. So now we are still in the multiple linear regression. Suppose can finish this today. Yeah. Okay. Okay. So now we see the residual plot. Okay. The residual plot. Residual means error. Okay. So now we focus on the error now. Yeah. Okay. So take note because some of this may be useful, yeah, for you to do the test the assumption. Okay. So we discussed a bit just now. I mean previously test the problem, the problem of the multi-collinearity. Now we see 3 more. Yeah. Now. Yeah. So okay. So we are here. Okay. 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 So I think we can start. Yeah. Okay. So now we are going to see all this. Yeah. The residual plot. Again, the residual means error, means error term. Yeah. Okay. Okay. So a quick one. this like this. This is the particular linear regression model. Yeah, and error residual also refer to this. Error also same thing. Yeah. Okay. So depends on textbook. Yeah. Okay. We see this one now. Okay. So this is data. Okay. So and then what we do, we analyze. Okay, analyze and then regression and then linear. Okay. Okay, analyze residual, analyze regression, okay, and then linear. Okay, so we can use any combination, yeah, of the model for you. Of course, you must use your own data set. Yeah. So we use the satisfaction, yeah, as the dependent. Okay. So now I think we can use 12 until 16. Yeah, fine. Yeah, it include 5 independent variables. Yeah, from 12 until 16. Yeah. Now we got 5 independent variables. Okay. Okay. So if no problem, now we see next. Yeah. Okay. Okay. So this one nothing. Continue. Plot. Okay. See plot. Okay. We do histogram. Okay. Do histogram and then normal probability plot. Okay. And then so here you can choose Z residual. Yeah, you focus on the Z residual. Dependent means refer to dependent variable. Yeah. So Z residual means what? Means the Z score, yeah, for the residual. The Z score for the residual. Okay. Okay, no problem. Now we see continue. Yeah. Then save. So for save, now we want the residual, we want to standardize. So residual, we want to standardize. Okay. So if no problem, now we click okay. Continue. Yeah. Okay. Option. Nothing. Okay, then nothing. Just click okay. Okay, so we get the output here. Okay, I give you 10 seconds. Make sure you get the same thing. Okay, so if no problem, we see one by one. Yeah. Okay, so this one actually nothing. You know how to do already. The beginning part. Now we see here, okay, the histogram. Yeah. Okay. So can you see this is quite similar with what we discussed, what we discussed in the previous classes. Yeah. So actually no need no need to use word. So from here you know already the normal curve. You can see the normal curve. Yeah. Okay. So let's say the histogram, yeah, is quite fit with this the normal curve. Means the data, the residual is normal. This is what we use the first one, histogram, of the standardized residual. Okay, means you see either the error they follow the normally distribution or normal distribution or not. Which is we can see either the residual they actually follow the normal distribution or not. Okay, this is what we can do using the histogram. The blue color is the light blue color is the histogram. Yeah. Okay. Means the normal curve actually come from the histogram. Yeah. So this one I emphasize quite a lot in the state class. I mean previously. Okay, previously. Okay. So from here still consider quite okay. Yeah. It means still consider quite normal. Yeah, quite normal. Any question on this? Okay. So if not, now we see next. Yeah. Okay. So this one actually is a PP plot. Can you see the expected cumulative probability and observed cumulative probability? So here still consider quite approximately, approximately normal. Okay, because some points, some data points, the blue dot representing the data point. Yeah, if all the data point fall on the straight line, the black color means it's the normal. But now still consider quite okay. You can see the standardized, the plot of the standardized residual. Okay, so still consider quite normal.
So to consider quite normal, I saw that the mean is close to 0 and the standard deviation is close to 1. So any threshold value that we can decide that this is not normal? Any indicator that we should look at?
Okay. Actually, this is not a very not confirm. Cannot use this. Okay, now. You know why? Because this is all standardized. Can you see?
Yes.
Because it is a standardized plot. Therefore, the standardized data must be like this. It must be 0, 1.
Yes.
Must be. Yeah. Therefore, example. Okay, example. Yeah. Let's say you buy something. Yeah. You go to shop, you buy something. You say you want 1 kilo of this something. The shop prepare for you. They'll say, oh, this is 1 kilo. Oh, therefore it's good, something like that. But cannot be because they follow your instruction. You want to buy 1 kilo, therefore they prepare 1 kilo for you. Okay now. So for this one, we actually ask the software to find the plot for this standardized normal distribution. Therefore, the data must follow this 0, 1. You see here, 0, 1. This diagram, right side top. Therefore, it's quite close to 1, 0, 1. Okay, now means we cannot use this as the any indicator, but we only can see the diagram. If the histogram fit to this normal curve, means it's normal. Okay, I give you example, not normal. Okay. Example is like this. Okay. Okay, now I use different color to represent the normal curve. So the normal curve, something like this. You can see, means the histogram, the bar actually not fit to the normal curve. Yeah, but here still consider quite okay. You can see, here this part a bit more, but the rest is quite close to quite fit to the normal curve.
It means it's just a visual inspection.
Yes, correct.
No indicator, no value one, just by visual
Yes,
inspection.
Correct. But it doesn't matter. Okay, I still can show you another method to see the data normal or not normal. Okay, so
yeah, because sometimes it could be, I'm not sure, it could be subjective to some.
you are right. Okay, you see this in the show. Okay. So now we discussed already two. Yeah, thank you. Okay, discussed already two, the histogram and also the PP plot. Okay, you see. Okay, I show you now. Yeah, the method. Okay. So. Okay, so it's here. Means now we see okay, before that, this is first the data view. Okay, remember just now we click save. Therefore, we created one column. You can see here. Okay.
Okay.
This one is the Z residual. Okay, so Z residual. So now using this, we have to test either it's normal or not normal. Okay. Okay. So now we do analyze. Yeah. Okay. How they do this? How they do this? Yeah. How they do this? Yeah. So they use this formula. Yeah. Z equals to x minus mu over sigma. Okay. So they convert the x to z. Therefore, the mean must be 0. Okay. The mean must be 0. Yeah. Okay. But even the mean 0, yeah, the standard deviation is 1. Doesn't mean they follow 100%. It doesn't mean they 100% normal. Okay, we see now. Analyze, explore. Yes, correct. It's here. Now we want the standardized. The Z residual. Okay. You click here, both. Okay, both. Means you see the diagram and also statistics. Yeah. So we can see both to determine either the data is normal or not normal. Okay. So this is residual. This is residual only for the model just now. Remember, we include 12, x12 until x16. Okay,
Yeah.
this is the model. Yeah. Yes, us now? Yeah.
Yeah.
Nothing else? Okay. So if nothing, we continue. Yeah. So this in this model, we can get the error term. Yeah. From the error term, we save it. We save it here. Okay, in the last column. Okay. And then now we use this data set. We see the residual normal or not normal using two methods. Okay. First is the plot, and also the statistics. Okay. So nothing. Okay, this one. Okay, can you see? This you test for the normality with the test. Therefore, two lah. The plot and also the test. It's not too important. No need. Yeah. Okay. Option. Okay, that's it. Okay, okay. Click okay. Okay, if no problem, means all can follow. Yeah, you click okay. Okay, so we see this one now. Yeah. So this is a test statistics. Test statistics for us to test either the data is normal or not normal. Okay. So be very, very careful. Be very, very careful. For this normality, the hypothesis is different. Okay. Okay. So the data is normally distributed. Okay. Yeah, is not. Sorry, wait. Yes, correct. Okay. So this is hypothesis. Okay. Normally, got student want to argue with me. Normally, yeah, okay, but it's okay. I'll show you. Yeah. Normality. Okay. Distribution, normality, hypothesis. Yeah. So the hypothesis is correct. Yeah. Okay. So can you see here? Yeah. So the null hypothesis said that the population is normal. Okay. Therefore, it's the same with what we have this here. Okay. Data is normal, and then the alternative hypothesis says that data is not normal. Okay, it's not normal. Okay, like this. Okay. So don't worry, I explain. So previous intake got student ask me, actually like this. Yeah. This in general, okay, in general, normally we aim to reject the null hypothesis. Yeah, let's say for F test, T test, we reject the null hypothesis, we are happy. Okay. But for testing of assumption is a bit different. Yeah. So testing of assumption, we aim not to reject the null hypothesis in general. In general, okay. There's still some testing that we actually assumption, but we prefer to reject the null hypothesis. But normally we don't want to reject the. I mean, we aim not to reject the null hypothesis. Okay, therefore two categories. Again, this one only general. Okay, so this is hypothesis. Okay, any question? Yes.
So can we use a skewness value to determine whether the data distribution is normal or skew?
Okay, good question. Yeah, actually, skewness or kurtosis is good, but too basic. Yeah, too basic. Some you see this one they develop some many testing. Yeah, at least I can tell you at least 30 testing to test either data is normal or not normal. Okay, at least 30. Yeah. Okay. I know below 10. Okay, I know few only below 10. 10 method. Okay. I mean, no means I know how to do testing. Okay. Okay. So from here, we see the return. We are here. Yeah. So here got two testing. Yeah, either one you use, we actually cannot reject the null hypothesis because p value is large, more than 5%. Here is 0.2. Here 0.328. We cannot reject the null hypothesis. Therefore, data is normal. Okay. So again, you can also use this in your assignment. You're testing the assumption. Yeah, one of them is that the error should be normally distributed. Okay.
Okay.
Okay. Yeah. So of course, can also use PP plot. Yeah. So only few numbers. Yeah. Few data point far away from the straight line. Therefore, still consider normal. Yeah. Okay. So it's okay. It's not it. Yeah. Okay. Okay. So if no question, so means we done already for this residual plot. Okay. Yeah. Okay. So now we see next. Yeah. Okay. Again, as usual, when it comes to hypothesis, you write a little bit more. Yeah. You compare the p-value, and then you write you say that the p-value is more than 0.05. Therefore, we cannot reject the null hypothesis. Therefore, we follow the null hypothesis. Okay. Therefore, the data is normally distributed. Okay. So, if no question, now we see. This one actually also discuss a little bit. Yeah. Okay. Also discuss a little bit. You will see. So we can add or we can separate sample. Yeah. Remember, if 1 until let's say 12,000, you can make it become 6,000 and then 6,000. You do testing. So you can separate sample. So everything model A, you have what 12,000 observation. Model B, 1 until 6,000. Therefore, still have 6,000. The sample is 6,000. Okay, 6,000 sample. I mean respondents. In the model B, model C also 6,000, but 6,001, 6,001 until 12,000. Like that, right? You compare the full model. Model A, we call it full model. The model B and C, we call it subsample. Okay. Okay. So, so you see the calculating the price statistics. This is actually also discussed a little bit previously. What we do, we can remove one company. Let's say you have 50 companies from South Korea. Yeah. Okay. South Korea is the best example because Samsung is very important. Okay. Malaysia, we do have the very important company. Yeah. Even Petronas not considered too significant as compared to Samsung in South Korea. Okay. So remove one company, you testing like that. Finally, you can get the price statistics. Okay. And then you can also compare the regression model. Yeah. Let's say you have 5 independent variables. Yeah. You can, this is model 1, full model. Model 2, you only put in 4 independent variables. Like that. Okay. So example A, B, C, D. Here you take B, C, D, E, like that. Okay, you compare the models. Forecasting actually, the term that you use may be a bit different compared to the term that I use. Okay, yeah. I think different. Yeah, it's okay. I can discuss a bit now. Yeah. Then, anyone learn already time series in forecasting before this? Anyone? Okay. No, it's okay. So this one, this is a quick revision. Yeah, you learn this in time series and forecasting. Suppose. Yeah. Okay. You see now? But the term you use is a bit different. Yeah. So for me, well, maybe that's different between the time series. Yeah, the difference between data science and statistics. Okay. So you see, let's say your data, you got data. The data is from year 2000 until June, June 2022. Okay. Now you do data analysis only for year 2000 until 2021 December. Let's say it's a monthly data. Okay. So you do testing for this. Okay. Okay. So this first part of the data, for I think you call this train data, right? Anyone? Or training data, something like this, something like that. This is your term. For me, for us, we call this in sample. Yeah, in sample data. Okay, in sample. Okay, and then use this to forecast this. This actually we know already. Just to do testing to see either the model good or not good. Okay, this one is also for validation. You to test the model good or not good. Okay, so we call this out of sample. Yeah, for us, we call this out of sample data. Okay. I don't know this one what you call. This one I think you call it train data, something like that. Okay. So this is what we, but it's okay. Yeah, just a bit different. Doesn't matter. Yeah. So okay, if no question, now we already done chapter 2. So now we see. Okay, done. Okay. So okay. Okay. So a quick one. Why should simple regression be used? When you have only one independent variable, then you use simple. Okay. Use multiple. Sorry. Another one is when the dependent, independent, or metric. Okay, all metric variables. Okay. So for your assignment, your data, your variable cannot be only 2 categories. Cannot be 0, 1. Example 0 means poor, 1 means excellent. Actually cannot. But Likert skill still okay. Because Likert skill, they have many minimum 5 categories, 1 until 5. Because you want the variation. You can see. Okay. Let's say as I mentioned previously, the lane size of a country is not a good independent variable because the lane size never change too much. Normally, okay, normally. Okay. I know some country the lane size change some, but normally no change in general. Okay. So you want some variation, therefore you prefer a metric but with some variation. 0, 1 cannot. Okay. Multiple linear regression, also same thing, but minimum 2 independent variables. And then dependent and independent must be both and metric, okay, metric variable. Okay. Why? So why? Because cause effect. Okay, cause effect. Okay. And then because because we know in real life there are many factors can affect one factor. Okay. There are many factors that can affect one factor. Okay. So example, your your consumption behavior, of course, affected by your income, also your family size. You see, also your parent income. Why not? This your parent income quite a lot. Therefore, you may feel more free to spend. If not much, you need to support them. Maybe you give them some money. You spend a bit less, something like that. Okay. Therefore, many factors will affect your consumption behavior. Okay. So, it's number 4. Yeah. What level of statistical significance we normally use 5%? Okay. And R square, of course, 95. So say no, R square not much. Minimum half lah, minimum half. Okay. Again, R square not too important compared to F. F is very, very important. Okay, Fisher. Yeah, Fisher test. How do you use? Okay. How do you use? So of course we can interpret. Means we use the regression coefficient is a unit. Okay. So example, let's say the coefficient, we see two things. First thing is the sign. Yeah, either positive or negative. Okay. Either positive or negative. Okay. And then also the magnitude. Okay, the magnitude. Okay. So let's say you this example, okay, this example, okay. Do you agree if you are in that field? Okay. Let's say you advertise, yeah. You advertise a lot on the paper print, yeah, and also TV, yeah. I mean the printed newspaper, okay. But the sales cannot increase. Therefore, this is independent advertise, yeah, in this newspaper and TV, yeah. But the sales actually drop because many people cannot see, or maybe you're targeting wrong market. Okay, okay. So maybe some people got no TV, they watch video using YouTube and so on and so forth. Okay, before your sales drop. From here, its sign is negative. Means you should know you should stop advertise in newspaper and also TV. Okay, this is a sign. Okay. So and then you also see the magnitude. Okay. So we see magnitude. Okay. Let's say you advertise one AV 1000. I know advertise in YouTube is quite expensive. I know that. Don't worry. Okay, you advertise AV 1000 ringgit, yeah, in YouTube. Yeah, the sales increase 3000. Example. Okay, example. So means from here you know you actually earn 2000 ringgit is the magnitude. Means you can do some calculation to see worth it or not for you, profitable or not for you to invest to advertise in the YouTube again. Of course, 1000, 10,000 is very good. You can see you increase 1000, the sales increase 10,000, therefore it's very good. But how about 3000? Maybe not profitable. Okay, because you must cover other things. The product, you produce the product or maybe service and so on and so forth for money. Okay. these are some example. Okay, how to apply. Okay. So okay. Okay, so we've done already this chapter. But first we see tutorial. But before that, any question you want to ask for this chapter? Okay, if no, now we see the tutorial. Okay. Anyone just joined? You let me know. Yeah, I think got few absent. Yeah, still got few. So we see the tutorial now. Yeah. Okay. So I think you will try. Yeah. Exercise. Yeah. How will you explain the relative? Because this one already discussed. Yeah. Just that you can remember, then you should know. I think discuss a bit also just now in the first 30 minutes. Answer. Okay, wait.
This one is the standardized coefficient.
Yes, correct, very good. Okay. So you see, I answer the question asked by Guan Sing. Okay. No need. You no need to do normalize because you just use the original data. If you want to do normalize, you can do it in the SPSS. Then they will give you another column like this. Can you see? Then you use this to do testing. Yeah. Okay. Like that. Means to test either the data is normal or not normal, and also other things. Okay. So, no question. Okay. So your answer is correct. Before we use the standardized. Okay, standardized normal standardized coefficient. Standardized beta coefficient. Okay. So to compare to see which independent variable is affecting the dependent variable more. Okay. So this to answer part 1. Yeah. If no question, we see next. Okay, number 2, a little bit technical. I explain to you. Yeah. Okay. Why? Yeah. Why you must do testing? Yeah, must examine the assumption of linearity. Yeah, when using the regression. Yeah. Okay. So because okay. Okay. So because when the statisticians they develop this multiple linear regression, they have this assumption. They assume data is linear. Okay. They assume that there's a linear relationship between the independent and also the dependent. Then they develop it. Okay. So yeah, that is okay. So therefore, X supports linearly affecting the Y under the classical linear regression model. Okay. Okay. So therefore, this one is only correct when the data is normal. It's linear. If not linear, but you still want to use this model, therefore it doesn't fit. Okay. You can think of one example. Let's say your car suppose using NGV. Okay, different country, different system. I know we call it natural gas for vehicle. That means it's okay. So natural gas for vehicle, natural gas lah. Okay. So suppose use NGV, but you put in petrol. What happen? You can say something. Your car cannot engine cannot start, or maybe other problems. It doesn't fit. Like that lah. Okay. So this why you must examine the assumption first. Okay. Okay. So if no question.
So sir, we examine the assumption by looking at the data visually, right? I mean, if it's almost linearly, or if it's a quadratic or other polynomial, then it's not possible, right?
Okay, you can do the scatter. Okay, good question. Okay, we do this now. Yeah, good question. Okay, so we do this now. Yeah. So linearity, we can just do the scatter plot. Okay, we do this now. Yeah. So graph, and then you can see the log. Okay, scatter. Yeah. Okay. Okay. So we use this. Remember, we use the same model just now. This x12 until x16. Okay. So simple scatter, and then define. Okay. So now the y always dependent. Therefore x17. Okay. The y always dependent. X we use 12. X12. Actually, we should produce 5 diagrams like this. Each diagram using different independent. Okay. So you can set the title by your own later. Yeah, but now we focus on the testing. Okay. Like this. Okay. Therefore, no relationship, but it's not considered linear. It's no relationship between these two variables. Cannot consider linear. Okay. But again, it's important for the capstone, not much important for the assignment. Example, let's say your data not normal, not linear, you still can proceed. Don't worry about that. Just that you have to make sure that you know how to do. And you know the reason. Okay, for assignment. Okay.
Okay.
For capstone, yeah.
No.
Simple answer. Okay. We already discussed. Okay, you already discussed. Yeah. Okay. Of course, I can prepare, but I don't think I have time to prepare the answer. Yeah. Okay. So, yeah. Next. Yeah. Number 3, I think also not too easy. Yeah. Okay, it's okay. I can discuss now. Yeah. How can non-linearity be corrected, yeah, or accounted, yeah, for, yeah, in the regression equation? Yeah. Okay. Okay. So we have many method. Okay. Many method. Okay, I show you 2. Yeah. So first one, you can take log. Yeah. You can take log for the data. Okay. So to make it linear. Yeah. Okay. So this, let's say, data is not linear. You take log, maybe linear. Okay, you can try log. You can try also log or log. Okay. So we prefer this because this one will be easier to interpret. Okay. Okay. So for the log will be easier to interpret. Okay, I'll show you now how to interpret. Example, I think not going to see too much, but at least one. Okay, at least one. Yeah. So let's say log y equals to alpha plus, let's say 3 log x. Okay, this is the result. Okay. So how to interpret the 3? How? Yeah. When okay, when x increase by 1%, yeah, the y will increase by 3%. That's it. Okay. So you can try to do this. Yeah, take log for both sides. Therefore, this is the interpretation. Therefore, the beta coefficient. Remember, previously we use the unit, either kilogram, ringgit, or whatever. But now we should, let's say double log, because it's double log. We should use this method. It means x increased by 1%, y increased 3%. Okay, so this is the first method, okay, to handle the non-linearity. Okay, so second method, okay, so second method will be, second method we can increase the sample size. Okay, we can increase sample size, then we test again. Okay, like that. Okay, so it's, especially when your data is not balanced, yeah, yeah, not balanced, I think should be the same. Should be the term also you use, yeah, in data science module. I mean other data science module. Yeah. So not balanced. Example, okay. Example, let's say in your data, female and male. Yeah, female let's say 500, male only 100. It's not too balanced. You can increase the sample size for the male. Then test again. Maybe become linear. Okay. Yeah. So this is the some method that we can use. Okay, to handle the non-linearity. Okay, but again, for your assignment, you don't waste your time too much. You just do the testing, even non-linear, you just interpret the result, you still proceed with other testing. Yeah, otherwise, you cannot finish on time. Yeah. You need to do work, also got test, I also quiz. Yeah, okay. So this is number 3. Yeah, any question? Yes.
So can we use clustering or grouping or binning to eliminate non-linear?
Again, what method? I think
Clustering or grouping on the data. If the data is scattered too much, then we cluster it or group it. Is it possible?
this I don't know. Which topic you learn this method?
Data management. I'm not sure whether it can be used for this case or not. In data management courses.
Okay, okay. If you learn this before, therefore you just you use it. If you want, you can use it. Then you put some citation. Then you can refer. Okay. Maybe it's the other technique. Some technique that I'm not really sure. Yeah, but anyhow, if you learn this, you can put some citation. But text citation you don't say the notes from lecturer. You should mention from textbook. Yeah, like that. Right? Then still okay, can be used. But again, assignment no need. Don't waste your time. Okay. Yeah. So by this method is new for me. I never use this to handle the non-linearity. Yeah. Okay. Okay. If no question, now we see next. Yeah. Okay. Okay. Can you try now? Will you find a regression equation that would be acceptable as statistically significant, and yet offer no acceptable interpretational value to the management? You try first now. This result is very good. Yeah. Okay. Using technical term. Technical term meaning that statistically significant. Okay. But practically not significant. Practically. Okay. Try now. Yeah. Okay, another 1 minute. In case no answer, I give you example. Okay. So, okay, yeah. Thank you. Okay. Very high correlation between amount of money, yeah. Okay, on buying inventory and the number of inventory that they have. No, this correlation. Yes, correct. This one it can be this correlation, yeah, but still meaningful, yeah, still meaningful because no use. This is significant but no use, yeah, for the management. Yeah, anyhow they want to do business, they must spend money to buy inventory, okay, for any shopping complex or maybe factory, yeah, okay. So be careful. Make sure you know the difference, yeah, because in your statement you mentioned two things, yeah, but actually there are two different idea, correlation and also regression. Okay, so correlation is a number that in between -1 to 1, yeah. Okay, there's some relationship between these two, but there are two different methods, yeah, in statistics, yeah. Okay, let's say the value is high, means is positive, positive relationship. Here can be will be negative. A positive, a negative, positive. In between is no relationship. Okay. Okay. 0 means no relationship. Let's say here 0.23, meaning that is a weak positive relationship. Okay. But for this topic, we focus all on the regression. But maybe we discuss a little bit correlation, but it's different thing. Okay. So regression will be equation that we've seen many times in this chapter. So that is okay. And then can you see correlation, no equation. And then regression must be cause effect. Must be you can explain the effect of the independent on the dependent. Okay. So you find one or two article for this for your assignment. Okay, for your capstone, if you want to use this, you should have more articles to support your point, so that you can put in this variable. Like that, okay? Different a lot. Okay.
So can I say, sir, if a more technical term correlation is talking about the R square, regression is talking about the beta coefficient?
No. Correlation is not about the R square. Correlation is only the R. Yeah, small lowercase r. Okay. Okay. R square is also under regression. Okay. Yeah. Correlation only R. Yeah. Only a number. Of course, we are going to use this also in the next chapter. Next chapter, the factor analysis. Yeah. Information know the difference. Okay. Only a number. Okay. So the number between -1 to 1. Okay. So okay, if no problem, now we see. But the example is good. Okay, it's good. Confirm. You must buy more. Yeah, because you want to do business. Okay. So therefore, for the company, they will feel this suggestion is useless. Okay. So therefore, it's good example. Yeah. Thank you. Okay. Employee job satisfaction affected by gender and age. Yeah. Okay. Very good. Okay, this is very good because you cannot change people's gender, also the age. Okay, I mean in Malaysia. Okay, I know some other country they can change gender, but in Malaysia cannot. Okay, it's illegal. Okay, so age cannot change. Okay, therefore yeah, good. Yeah, okay. So therefore the result may be significant, but also meaningless. Okay. Beta is definitely larger than 0, but serve no purpose whatsoever. Okay. No. No, you give a general example. Yeah, if it's correct also. Yeah. That means you just explain the question. Yeah, you did not give example. It means can say for this one. Yeah, okay. So yeah. Holiday shopping. Okay, during holiday shopping confirm increase. But this one meaningful for company. So meaningful for shopping complex. Yeah. So you can see normally holiday they got many promotion, discount and so on so forth a lot. Yeah. So it's meaningful, yeah, for the company. Yeah, especially shopping complex. Yeah. Okay. Therefore, statistical significant, the sales will be increased a lot during holiday, but also important for them to do some preparation. Right? Okay. Also, prepare some more food or more stock and so on so forth. Okay. Okay. Well, good. Yeah. Many example. Okay. See. Okay, so logistic, you talk about the this issue just now, but we cannot say correlation is under regression. Yeah, but we can say like this. We can say like this. Yeah. Okay, like this. Regression and correlation. Yeah. So in certain thing we need to discuss correlation when discuss regression. Okay, like this. Okay, but if correlation is not under regression, we never say like this. They are two different things, but sometimes they have some relationship. Yeah, like that. Okay. Okay. So if no question, now we see. Yeah. Thank you. Okay. We see next. So yeah. Anyone want to try or find? This one some of you can give answer because already discussed in classes. Okay. Okay. Remember interval. Interval you got two examples. Yeah. First is the temperature. Yeah. Example. Now I think maybe outside maybe 25 degrees Celsius, like that. Okay, temperature. So and then year, yeah, okay, 2022, 2010, okay, the year. Okay. These two are considered interval. Yeah. Versus dummy. Yeah. So any comment from you about these two things? Yeah, try now. Only 2 points actually. Okay, only 2 points. Okay, another 1 minute. Yeah. In case no answer, I will show you the answer.
So maybe I can try.
Okay, good. Yeah, try.
The interval scale predictor, when we interpret, is whether we can tell there's a incremental effect on the dependent variable. Whereas for the dummy predictor, is either whether it has effect or no effect. It's not incremental, it's like very absolute.
No. No.
then yeah, let others try.
Okay, okay. Okay, try. Another 30 seconds. Okay, check the answer. Yeah, okay, we see. Yeah. Interval skew predictor variable will show the proportionate increase or decrease against DV. Dummy will show two equations here for each 0 and 1. Okay, this point is good. This point is good. Therefore, in the interval scale predictor, you only have one equation. Yeah, but in the dummy, you got two. Yeah, so means different two categories. Yeah, each category have their own equation. Okay, yeah. So okay, it's good. At least for one point. Yeah. Okay. So and then of course one more thing, when you interpret the interval scale predictor, you only have interpret once because only one equation. Yeah, but for the dummy, you got two. Yeah, each you must interpret differently. Okay, this is the difference. These are 2 points. Okay, to answer this question. Okay. Okay, so we done already for the chapter 2. Yeah, multiple linear regression. Okay. So therefore, let's say any part you are not sure how to answer question number 1, you can ask in the next class. So like just now, what student asked about the assumption. Okay, you test all the assumption that we discussed in this class. Okay. Okay. So if no question, we see factor analysis. Okay. So factor analysis, of course, today not going to use the software, but maybe tomorrow. I'm not sure, but we see how. But instead, we also use the SPSS. Okay. So the point is that we also use SPSS here to do the data analysis here for the factor analysis. Okay. Okay. So now we see. No question for the previous chapter, so we continue. We see new chapter now. Yeah. Okay. So this is for important for question number 2. Yeah, and also some some quiz or test like that. Okay. Okay. So okay. Some maybe want to ask me also different between these two. Actually, it's like this. Yeah. It's like this. Yeah, see. So factor analysis and also principal component analysis. Therefore, these two are quite similar. Yeah, these two are quite similar. Also for the what they call the skew depth reduction. Yeah. Okay. Variable reduction. Yeah, variable reduction. Okay. Means from it looks like quite similar because we reduce the variable. Yeah, from let's say from 40 to 10. Okay, like that. Okay. But there's a difference. Okay, there's a difference between these two. Okay. Yeah. So okay. Okay, I can tell you a bit more. Factor analysis that we are going to discuss is the C. Yeah, C factor analysis, common factor analysis. Okay. Before we find some common factor among the variables. Let's say here got 30 variables. We find some common factors among 30 variables. And then for the principal component analysis, we actually try to find some important, some not too important. Can I see principal component? Principal component means the important component. Means we are going to do some ranking. Yeah. So the important component, 1, second, 3. It's like this. Therefore, the first 4 important, the rest not important. Okay, that's the principal component analysis. Therefore, quite similar. Okay. Okay. Therefore, it's also like the regression correlation, quite similar. But of course, we focus more on the factor analysis. Okay, as per the name of the chapter. Okay. But and then For this one, the similarity even more compared to the correlation and regression. Yeah, okay. So I mean compared to this, these two. Okay, so these two even much more similar, but this is different. Yeah, this is the main difference between the vector analysis and principal component analysis. Okay, so PCA, okay, principal component analysis. So we find the common factor, common variance under the vector analysis. Yeah, but the principal component analysis, we try to identify which group more important, some other not important, we ignore. Okay, if no question, now we see next. Yeah. Okay. So now we are going to differentiate vector analysis technique from the other multivariate techniques. Okay. So this was a good example to see the difference between this and also the multiple linear regression. So here is the interdependent, right? Interdependence technique. Okay. You needed all the variables same category, same level. Yeah. You cannot say which one is independent, which one dependent. Cannot. But for the chapter 2, it must clearly mention. You must clearly mention in your capstone or assignment which one is independent, which one is independent. You must only have one dependent under the multiple linear regression. Only one dependent. Okay. Okay. So if no question, now we see next. Yep. Okay. So for us, we are going to see confirmatory. Not common, sorry, not common. But this one is not common. It's confirmatory. Yeah. Okay. So therefore, it's a step ahead. It's a step ahead as compared to the E. Okay, correct here. E. E, E, F, A, and also C, F, A. Okay. So E means exploratory, C means confirmatory. Okay. So here we see this one first. Yeah, we see this in chapter SEM year later. Okay, now we see EFA first. Okay. So both actually both also factor analysis. You can see factor analysis. Okay, but we see EFA first, CFA later in the last chapter. Okay. Okay. Of course, we got 7 stage okay, to apply the factor analysis. Okay. This one not too important. Okay. Let's discuss a bit. So here is component analysis, means PCA. Okay. So factor analysis. See, actually here's common variance. Your factor analysis. So this one also quite important. You may see this in your assignment. Okay, we determine the number of factors here to extract. Let's say 30, altogether 30 variables. We want to group them to maybe 4. Therefore, we call it 4 factors, not variables, but 4 factors. Okay, therefore we call it factor analysis. Just explain the concept of allocation. Okay, we're going to discuss also. It's a technique for us to get the factors more easier. Okay, it's a technique for us to do the grouping more efficiently. Yeah. Okay. So how to name a factor? We discussed a bit in the previous class. Okay. Okay. Remember, they said some employee, yeah, they said that today I'm late to the office because of the car. My car is broken. Some say maybe okay, maybe petrol finish. Okay, and then some say the traffic jam. Yeah, some say the LRT delay. Example. Okay, all these transportation problem. Okay, transportation. You name it as transportation. Okay. So okay. Yeah. If no question, now we see next. Yeah. Okay. So now we see EFA. Okay, as I mentioned just now, this is the, we see EFA in this chapter, okay, EFA. And then CFA will be in the chapter, in the last chapter. Okay. So it's an interdependence technique. Okay, means now all the variables are same status. Okay, okay. Not unlike the multiple linear regression. Okay. And then the primary purpose is to define the underlying structure among the variables in the analysis. Okay. That means we can identify few important factors. Okay, from 30 become 4. Okay. So here got A, B, C, D. Okay, see, therefore the structure is better compared to 30. Yeah, okay. Okay, means 30, you do know, people do know, some variables actually they are quite similar, they can group together. Like that. Okay. So therefore we can know, we can define the structure of the among the variables in the analysis. Okay, so no problem. Now we see the concept first. Yeah. Okay. So we see as EFA, exploratory factor analysis, we examine the interrelationship among a large number of variables. Okay, let's say 30. Yeah. So means of course we know 30. Yeah. A, B, C, D example. A and B maybe have a strong relationship. A and C don't have. And so on and so forth. Okay. Therefore you can compute the correlations actually. Okay. So it means we use this as the measurement to see do they have any relationship among the variables. Okay. Okay. And then we attempt to explain them in terms of their common underlying dimension. You can see the common underlying dimension. It means refer to the common variance. Okay, the common variance among the 30 variables. Okay. 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 So these common underlying dimensions we call it factors. Therefore we call it, therefore this chapter is factor analysis. Okay. So can I see this now? Yeah, okay. For looks like different thing, but actually all under transport. Therefore easier for us to analyze. Or maybe for HR to do some analysis and so on and so forth. Okay. Before it's a data reduction, okay, data reduction or variable reduction, your technique. Okay. So that does not have independent and dependent. Means you cannot say which one is independent, which one dependent. They are all same level. Okay. But it's an interdependence technique in which all the variables are considered simultaneously. Okay. Okay. So it's okay. At least can see these two. Yeah. Okay. So here got 9 variables. Okay, 9 variables. And then we see few things. Can you see its correlation matrix? Yeah. We can get this table also from the, of course, it's easily from the SPSS. Okay. So here's for the store image elements. Okay. So it's how people view the store, the shopping complex, and so on and so forth. Okay. Here I've got 9 variables. V1 until V9 means same thing lah. Okay, refer to this. V1 is the price level. Price level with price level must be always 1. You can see. Therefore, the diagonal always must be 1. Always. Okay. Why this matrix? They only show us the below the triangle, not the upper. Because if they will show you the same value. Example, let's say 1, 4. 1, 4, therefore is 0.47. We needed correlation between 1 and 4 is equal to correlation between 4 and 1. Fair enough. You and Mr. Lee go and watch movie. your friend. Okay, you and your friend Mr. Lee go and watch movie. Mr. Lee and you go and watch movie. Same thing. Okay, same thing. Okay. Therefore, no need to show the upper. Okay. Okay. Any question so far? No, you finish. We can discuss at least two. Yeah, this one and also this two tables. Okay. If not, we see next. So, okay, here positive, all positive. The linear correlation between negative 1 here to 1. Okay, 0. Okay, like this means strong. Means any correlation value that near close to 1 consider strong relationship. Okay, small close to negative 1 also strong relationship. Okay, so here all are positive. Some high, some strong, some weak. Okay, so example, this is considered strong. It's 0.7 and above. Okay, another question. Okay, someone to ask me, what's the threshold? Yeah, but therefore depends on the article. Some say 0.7, some say 0.6. Okay, so therefore, in general, you can use 0.6 or 0.7. Yeah, but obviously, I try to use some number that is different a lot. Example, 0.771 and also 0.281. Okay, so this is quite strong, it's quite weak. Okay. 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 So now we want to do grouping. Yeah, we do few grouping. Example, some maybe linked to product. Yeah, product, some maybe they want the service. Yeah, see, okay, service good or not good. Okay, so some maybe they want the atmosphere, and so on and so forth. Okay, some focus on the price of the product. Okay, so but here it's not easy for us to see the relationship. Before we can do like this. You see, from here, we can do correlation, but not easy to find the group. Here, we can find the group. Can you see 3892 is one group. So this is one group. Because among them, the correlation always very high. Let's say we use 0.7. Always more than 0.7. 0.733, 0.774, and so on and so forth. Among these four. Yeah. V3, V8, V9, V2. Okay. So let's say here means the relationship between the V8 and also V9. Install atmosphere and also 8 is here, install service. Okay. Example, what they call the promoter really polite and so on and so forth. They very smart and so on and so forth. Okay, all the install service. Okay. Okay. So meaning that, okay, now we can introduce one term, okay, rotation. Okay, rotation, yeah. So by using correlation, we can only get this. By using rotation, we can get this later, we see. Okay, the idea of rotation means they will make our life easy, make us easier to interpret, to find the vector. Okay, so therefore, here got three vectors. 6, 7, 4, another vector. 1, 5, another vector. Okay. So means you can find maybe three vectors now. Okay. Well, but maybe not too easy. Yeah. Now here you can easily to find the grouping, three groups, three vectors, but not easy to find the term. Yeah, the name of the vector. Okay. So
sorry, sir. Can SPSS help us to sort according to this kind of pattern?
Yeah. That's why I mentioned rotation. Rotation is a function in the SPSS. We do this. Yeah. Don't worry too much.
Thank you.
Okay, I can show you now also, but not testing. Not testing. Just show you the one is available. Analyze dimension reduction vector. Okay, and then you see rotation. Okay. Yeah, you see this, we see the edge cases later. Yeah, not today. Yeah. Now we see the concept first. Okay. Okay. So if no question, I think this for today. Yeah. So this one next class. Next class we see tomorrow. Okay. Next class will be tomorrow. Okay. Okay. This one tomorrow 7. Yep. Okay. So for those who joined a bit late, attendance, anyone? No. Okay. If let's say you remember you don't mark, you can let me know. I mean DM not here. Okay. The two things to update. First thing, already uploaded the assignment question, okay, to the Moodle. Okay. Due date 17 October. Okay. Second thing, the what they call the timetable. Yeah, for the weekday class. Yeah, now we change to 7:30 to 9:30. In case anyone cannot, you can PM me also. Okay, you can PM me. Yeah, let's say got personal or whatever. Okay. So it must be everybody okay. Let's say one or two students cannot use the what they call. But of course, must give reason lah. Okay, don't just simply say cannot. Okay? But if no objection, we use 7:30 until 9:30. Still 2 hours. Okay. Okay. Any question? Yes. Last call. Okay. If no, okay, I read your name. I mean, so the student, no, this one full. This one full attendance. Okay. It's okay. Another 3 minutes. Yeah. So here got 2 students in this group. Shin Jong Seng.
Yes, sir.
Oh, you're here. Okay. Okay.
Thank you.
Okay. Why something wrong Still got 1. Oh, how come? Oh. Okay. But already full. Okay. So one more student. Okay, Jenna, are you here? Okay. Okay. So if no, see you tomorrow. Yeah, 7:30. Yeah.
Thank you, sir.
Thank you.
Right. Thank you, sir.
Yeah. Thank you.